we are leaving the world of solutions behind, and we are getting into thermochemistry. So this is a subject that you will look at now in chemistry, and then you'll hit the same subject again in physics next year. So this will come to you twice. You'll see a lot of these terms and a lot of these principles again. And actually, I think you even got a little bit of it last year in physical science. So by the time you graduate, you will know thermochemistry and thermodynamics really well. We're going to hit it now in the chemistry sense. So here are some terms that you will need to know. I'll give you a moment to write this down. So thermochemistry is the study of the interactions of matter and thermal energy, or heat. So we're going to be looking at when a chemical reaction happens. Does it give off thermal energy? Does it absorb thermal energy? Maybe it does a little bit of both. Maybe it absorbs some thermal energy and then releases some. And we're going to be talking about how a chemical reaction responds with matter and exchanges thermal energy. That's thermochemistry. Thermal energy is measured in joules, and a joule is a unit that you have seen once before. You saw joules back in physical science, back when the Earth was cooling 2 years ago, and you took physical science. The unit there should be familiar with to you. A joule is a relatively small amount of energy, so you will sometimes see energy expressed in thousands of joules or a kilojoule. This is a more usable quantity of energy for average things that happen. The total thermal energy of a system is called its enthalpy, and that's a weird word. Enthalpy is the measure of the amount of heat or thermal energy resident in something. So, you have a certain enthalpy, how much total thermal energy is in your body. And your total enthalpy is different than, some other objects like this bottle, which has cold water in it. So it has a very low total enthalpy because there's not as much thermal energy in it. Enthalpy is the quantity, the total quantity of thermal energy resident in an object or in a system. And this weird word has a weird abbreviation. We use J for joule and kJ for kilojoule, and that makes sense, but H for enthalpy, that's not very helpful. There's an H in the word, but it's right in the middle, and you don't think of the word, or you don't think of the letter H when you hear the word enthalpy. So that's one of the things you just kind of have to get used to seeing, and I'm sorry, it's an H. I didn't make it up, but I guess E is already taken, so there you go. Thermal energy, which changes the temperature of a system, is called sensible heat. You can sense it when you add thermal energy to an object and it gets hotter. That is sensible heat. The opposite of that is something, not the opposite really, but a different kind of response to receiving thermal energy is thermal energy which does work or goes into a phase change. Then that's called latent heat. So, for example, I can take a piece of ice that is at -10 degrees Celsius, and I can heat up that piece of ice from -10 degrees Celsius to 0, and I have made the ice get warmer. And so that is sensible heat. The ice used to be -10 Celsius, and now it's 0. So sensible heat, I could have sensed that it is getting warmer. But then at 0 degrees, if I keep adding heat to that ice cube doesn't get any warmer. The ice cube starts to melt. And the heat that I'm adding to that ice cube is not going into making the ice cube warmer. It's going into turning the water from a solid to a liquid. And so that is latent heat. It's heat going in, but it's not raising the temperature. It's doing work on the ice or work on the water. So latent heat does work instead of raises temperature. Sensible heat raises temperature. Latent heat does work on the object or on the system that you're adding the heat to. So there is a latent heat of fusion, and there is a latent heat of vaporization. Okay? And so latent heat of fusion has to do with melting and freezing. So if you were to measure the amount of heat that it takes to melt an ice cube from 0 degree ice to 0 degree water, you would have measured the latent heat of fusion for water. And we would express that as delta H. Delta means change in. So change in enthalpy, change in the total amount of heat available in that system, right? Change of heat, and then we put FUS at the bottom as a subscript to represent heat of fusion. So this is the energy that it takes to melt something, or backwards, it's the amount of energy given off when something freezes, absorbed when something freezes. So the same amount of energy that it takes to melt 1 gram of ice at 0 degrees into 1 gram of water at 0 degrees is the same amount of heat that you would either absorb from the water or the water would give off when 1 gram of 0 degree water turned into 1 gram of 0 degree ice. So the phase change either direction has the same quantity. It gives off the same amount of heat when it melts as it absorbed when it froze. Just kidding, other way around. Gives off the same amount when it freezes as it absorbed when it melted. There you go. Now I said it right. So delta H FUS. Similarly, delta H VAP, the latent heat of vaporization, is the heat change between a liquid and a gaseous state. So the amount of heat energy that it takes to turn 1 gram of liquid water at 100 degrees Celsius to 1 gram of water vapor at 100 degrees Celsius is the amount of, the heat of vaporization. And these are both latent heats because the temperature isn't rising, phase changes, it's changing, okay? And we always measure these in kilojoules per mole. How much energy does it take to move 1 mole of substance between the phase changes? So this is just an image of that. As ice gets warmer and stays ice, that's sensible heat. But when the solid ice melts into water, what we have here is 80 calories of energy going in to turn ice into water. But it's still at 0 degrees. This is water at 0 degrees, and so this is latent heat of fusion here. And then we can add 100 calories to raise that water up to 100 degrees Celsius. And then we can add 540 more calories to turn that water into steam, but still at 100 degrees Celsius. The vapor hasn't gotten any hotter. It's just turned from liquid water to water vapor. So this is latent heat of fusion. This would be sensible heat. This is latent heat of vaporization. Okay, and then all the numbers are exactly the same as you cool it down. If you took water vapor at 100 degrees Celsius and turned it into liquid water, that is condensing, and that is, again, latent heat of vaporization. The same 540 calories come out of it, and then you would cool it down and remove 100 more calories of thermal energy, and then you'd have water at 0 degrees, and then turning that 0 degree water into 0 degree ice, you would then remove 80 more calories. So latent heat of fusion is the same quantity, depending on which way you're going. And then latent heat of vaporization, same quantity. The sign just changes for which way you're going. Okay? Sensible and latent heat. You understand the ideas? Okay, dokie. And then, once again, the actual temperature does not change during the phase change. So if you have a solid that is very cold, you can heat the solid up, and as you add thermal energy, the temperature rises until you get to the melting point. And then when you're adding more thermal energy now, the temperature is not rising because this is latent heat that's just doing the work. Then it is liquid. You add more heat to it and the temperature rises. This is sensible heat. And then you get to the vaporization point or the boiling point and you keep adding more thermal energy, but this is latent heat again, and you're adding thermal energy while it's boiling. And then you get to the point where it's all steam or all vapor, and then as you add more thermal energy, you're now superheating the vapor. Okay, so latent heat does not change the temperature. Ice does not change temperature while it's melting. Water does not change temperature while it's boiling. All that more thermal energy you're adding just goes into phase change. Take a moment and write that down. So specific heat now. Specific heat, and we use CSP. And again, I don't know why it's C. Great. H means enthalpy and C means specific heat. But CSP is a quantification of the amount of thermal energy needed to raise the temperature of the material. So certain things respond really quickly to additional thermal energy. If you put a copper pan on a fire, the copper pan gets hot real fast. And that's why we use, that's why copper is a great metal to use for pots and pans, because it transfers thermal energy really quickly, and it very quickly reaches high temperatures. But if you put water in that copper pot and put it on the fire, the copper pot is responding to the heat of the fire and passing a whole bunch of energy to the water. The water temperature rises very slowly. The water temperature does not rise nearly as fast as the copper pot's temperature rises. And so water has a higher specific heat than copper. It takes more thermal energy to raise the same mass of that substance a degree centigrade. So specific heat has to do with how much energy you have to put into a material before its temperature starts to rise. Some things can absorb a lot of thermal energy and before their temperature goes up. Water is an example of that. Some things, their temperature goes up real quick, and copper would be an example of that. Okay, continuing from yesterday, thank you. So the thermal energy is calculated with this awesome equation. And if this is a delta, not an A, but it kind of looks like MCAT, and that's how I remembered it. The mass of the material times its specific heat value times the change in temperature that it experienced will give you the amount of heat energy that you had to put into that. So you take a piece of something, you stick it in fire, and it absorbs thermal energy, and its temperature will change based on its value for the specific heat. So the higher the specific heat value, the more energy it takes to raise its temperature. And this equation will be used by you many times here, and many, many, many times in physics. We spend a long time on that equation. So it will become your friend by the time you're done with school. Moving on here, this is just an example. If you were to add the same amount of, if you wanted to raise a kilogram of gold from 20 degrees to 90 degrees, and also you wanted to raise a kilogram of water from 20 degrees to 90 degrees. It takes about 30 times the thermal energy to raise a kilogram of water the same amount of temperature degrees as it does a kilogram of gold, because gold has such a low specific heat and water has such a high specific heat. So water absorbs more heat before it starts to change its temperature. Okay. Same reason why if you're cooking and you have a wooden spoon in a pot of soup that you're stirring, and you leave the wooden spoon in the soup and then come back to it later, you can grab the wooden spoon and keep stirring, and the wooden spoon doesn't burn your hand. But if you did that with a metal spoon, if you're stirring with a metal spoon in the soup, and you leave the metal spoon in the soup, and you go walk away and you come back later and just grab the metal spoon, it will be stinking hot. That's because wood has a much higher specific heat, and so it can absorb the thermal energy from the soup, and its temperature doesn't change very much. Metal, low specific heat, it absorbs the thermal energy from the soup, and it gets hot. That's why wooden spoons are good for soup. And then just so you've seen some of the ways that we express this, the value of C for specific heat is in units of joules per kilogram degree Kelvin. And some of the numbers here, the larger the number, again, the more thermal energy it absorbs before its temperature changes. So something with a relatively small number like diamond changes temperature very quickly. 500 joules of energy, which is not that much energy, will raise a kilogram of diamond. Boy, don't you wish you had a 2.5 pound diamond. A 1 kilogram block of diamond, 1 degree Celsius or Kelvin. So it doesn't take much thermal energy for that. Compare that to helium, which has a specific heat of 5,193. It takes 5,000 joules to raise a kilogram of helium, 1 degree. Okay, So a lot more energy there, and water is obviously a fairly large number as well. When you compare it to metals, have a fairly low number. Okay, let's do an example here. If 0.58 kilojoules, so that's 580 joules, if you were to write it out in normal numbers, of heat energy are added to 23 grams of ethanol at 13 degrees Celsius, what will the final temperature be? So it starts at 13. I'm going to calculate the change in temperature based on the value for C and the mass of the ethanol that I'm using here. I've got a table of specific heat values. This is given to us in kilograms and degree Kelvin. I have degrees Celsius. The width of a degree Celsius and the width of a degree Kelvin is the same. I don't have to convert. And so joules, kilogram, Kelvin. I have kilojoules. I need to get to joules. And I have grams. I need to get to kilograms. And I have Celsius, but I can leave it. So let's do this math. Ethanol is a specific heat of 2410 joules per kilogram. We have 0.58 kilojoules and 23 grams, but the constant is not given in those units. We need to do a little conversion. So 0.58 kilojoules is 580 joules. 23 grams is 0.023 kilograms. Okay. Now I can use my formula, and I've got my table out of the way. Q equals MC SP times delta T. Oh, sorry, it bled over. Somehow the font didn't like that size. Put everything in. Here's my value for C. Here's my value for Q. Here's my value for M. And then I'm just calculating delta T. Multiply it all across and divide to get delta T by itself. And I have a change in temperature of 10.46365 degrees Celsius. Okay? I need to correct for significant figures, so basically 10 degrees Celsius. If it started at 13, then the final temperature will be 23 degrees Celsius. So if I take that quantity of ethanol already at 13 degrees Celsius, and I add that quantity of thermal energy to it, and then I take its temperature again, it will be at 23 degrees Celsius. Okay, do you guys see how this math works? Questions? Okay. Enthalpy of reactions. Balanced equations that show the amount of energy absorbed or released are called thermonuclear equations. Sounds like we're going to blow up a foreign country, but we're actually just letting chemical reactions happen in our lab. It's not as dramatic as it sounds. Thermonuclear equations will demonstrate the change in enthalpy, or the change in thermal energy, right? And we use H for this. So the total change in enthalpy is equal to the change in enthalpy of the products minus the enthalpy of the reactants. So the energy available in the products that you start with, and then you subtract the energy, the thermal energy of the reactants when you're done. If you get a negative value for delta H, then it's an exothermic reaction. And there was more energy available in the reactants than in the products. It gave off energy. So that's exothermic. Positive values for H are endothermic. So that means that you had to add energy to get this thing to happen. Right? So here is, let me pause for a moment if you're still writing. Oh, I thought I had an example there. I guess I have an example later. Most compounds have an accepted value for what's called the enthalpy of formation. And that is how much energy does it take to make this thing? Or you could look at it as how much energy does this thing have because it is itself. So the enthalpy of formation, the amount of heat energy or thermal energy present in that substance. Now we have to assume that it's at a particular temperature, because thermal energy will change that. But when we'll say when it is formed, when we make it, what kind of thermal energy does it either absorb or give off? And there will be a value for it, okay? So for some substance, like pick something, sugar, there will be an enthalpy of formation value for sugar. And what that means is when you take carbon and hydrogen and oxygen from their natural native states and you arrange them to become sugar instead of carbon, hydrogen, and oxygen, what kind of heat is either absorbed or given off, okay? Most values are negative because most things are, the formation of most things is exothermic. It gives off heat energy as it is formed. There's a molecule of something is more stable than the free elements floating around in the universe. So most things have a negative value for the enthalpy of formation, and it's always composed to the energy of the component elements. Like I said, sugar as a molecule versus carbon, hydrogen, and oxygen as pure elements. The energy is given off when you make sugar, okay? And so it's a negative value. Most things have a negative value. There are some things that have a positive value, but it's definitely the exception. There's a table in your book that gives you the enthalpy of formations for lots and lots of things, and you will become very familiar with that table. This chapter, you will get to do a lot of calculations of enthalpy of formation or enthalpy of reactions, where you need to look up the values. Okay, so you'll get to know that. And in our labs that we'll do starting tomorrow, you will get to use this as well. Okay, so you'll be looking at how much thermal energy is resident inside a particular compound. And so to calculate the delta H for products and the delta H for reactants, what we have to do is look at the energy of formation, the enthalpy of formation for all the products, and then for all the reactants, and then subtract. So the summation of the values for the enthalpy of all the products minus the summation for the enthalpy of all the reactants. And then when we do this, we'll get a calculation for delta H, and we'll be able to say that this reaction is exothermic or this reaction is endothermic based on the values that we find. Okay, so now we do have some examples here. I'll give you a moment to finish writing. Okay, I had to make ammonium chloride for a lab, and I used hydrochloric acid and ammonia to make the ammonium chloride. So was the reaction that I did exothermic or endothermic? Well, you could do the lab, you could measure the temperature, mix it together, measure the temperature, and you can experimentally verify that it's exothermic or endothermic. But you can also calculate it and see if it's going to be exothermic or endothermic. So my reaction was ammonia plus hydrochloric acid gives me ammonium chloride. And so I need the enthalpy of formation values for all those things. And you can look it up in a table. And here's a table. This is actually the table that's in your book, okay? And you will get to become friends with it. So when I look up the table, the values here is hydrochloric acid at negative 92.31. Here is ammonia at negative 45.9, and here's ammonium chloride at negative 314.4. So you would look up the things that you need, okay? And once you've done that, you can take those values back. So HCl, NH3, NH4Cl. And you use them in this equation, right? So the summation of the products minus the summation of the reactants. Summation of my products, negative 314.4, that's easy. I made ammonium chloride, and it's the only thing in the products, so that's easy. Minus the summation of my reactants. My reactants was negative 92.31 and negative 45.9. Add them together, I get negative 138.21. If I subtract, now watch your signs. This is 7th grade algebra, pre-algebra stuff. But make sure that you just watch your signs. You're subtracting a negative, so that actually turns into an addition statement. So negative 314.4 plus 138.21 gives you negative 176.19 kilojoules. So my value for delta H is a negative number, which means it's exothermic. Okay, it released 176.19 kilojoules of energy when I did this. Watch your significant digits. Here I have 4 and 3 and 4. I should have only reported this as 3 significant digits. Sorry about that. That's a typo in the exam or in the lecture. Should have been 176 even kilojoules. Okay. So that's the kind of stuff that we're going to be doing in this chapter, and it gets deeper. We look at more forms of energy reactions later, but cell phones time. But this is good enough for now. So you'll be looking up values in tables and doing some addition and some subtraction. It's not hard math. It's just weeding through these large tables to find the numbers. Okay? That is it.